This is eddy current braking presented to you by Dimitri Yoranopoulos, Ben Creedon, and Cullen Brannon.
Through using kinematic equations, it was determined that we needed about 56 newton meters of torque to stop a bicycle moving at 40 miles per hour. For a proof of concept, we will attempt to provide about 14 newton meters of torque through only two magnets. The Scheiber model was used to determine the torquing brake provided by the braking system given the dimensions of the disc and magnet, the conductivity of the disc, the strength of the magnetic field, and the angular velocity of the disc. The ideal dimensions are listed in a table provided. These values were determined to provide the maximum braking torque needed for the bicycle moving at 40 miles per hour. The complete equation to determine magnetic flux density provided by the magnet is listed on the left. The equation can be simplified to the equation on the right if we use soft iron as a core. This is because of the high permeability of soft iron. The values for the number of windings, the amount of current, and the length of the gap are needed to provide 0.5 Tesla with soft iron as a core. The eddy current braking system can be broken down into three subsystems, which are the magnetic brakes, the sensors, and the control unit. The magnetic brakes will consist of the copper rotor, the electromagnet, and the test bench. The sensors will consist of the braking sensor, the rotational sensor, and the LCD display. The control unit will consist of the microcontroller. The copper disc was designed based off measurements determined by the eddy current math model. It has since been machined by Dimitri and Ben and is currently being fitted to the testing apparatus. Here is a picture of the core machined by Ben for the electromagnet. The height of 11 centimeters and the width of 13 centimeters were determined to accommodate the length and thickness of a 1,000 winding coil with 16 gauge wire. We were unable to find a vendor of soft iron for the amount needed to make the core, so we used 1018 steel instead. Because of the lower permeability of the steel, the amount of magnetic flux provided by the magnet will be less than the calculated value of 0.57 Tesla.
The purpose of the test bench is to characterize the actual hardware that we have built and see how it compares with our math model. This allows us to determine how effective our design is and make changes in the future if necessary. Currently the test bench is about half constructed, but all the components have been acquired, so it should be constructed by demo day.
The braking sensor consists of a power source and a potentiometer. This simple system is used to create an analog input that is fed into one of the ADC pins of the MCU. The braking sensor will serve as the primary input for the user and is the control sensor for the entire project. The rotational sensor consists of an IR emitter and receiver, which creates a field that sends an analog signal to the microcontrol unit each time the field is broken. The sensor serves as the primary feedback for the PID algorithm and helps control the overall system. The LCD used for this project will consist of the Stellaris Launchpad LCD Booster Pack EB LM4F120L35, commonly referred to as the Kintec display. This display will act as the primary output for the user and should display relevant information from the overall system.
We chose the Stellaris because it was readily available and we had training with it. The Stellaris has more than enough speed to run a simple PID algorithm and a display.
The software designed for this project will consist of four major components: the code for the braking sensor, the rotational sensor, the LCD display, and the PID algorithm. Each of these components will be discussed in their own corresponding sections. The software designed for the braking sensor consists primarily of the code necessary to ensure that the analog sensor can be connected to the ADC pin of the microcontrol unit. Once this has been accomplished, the PID algorithm takes this input value and uses it for the control system. The software designed for the rotational sensor consists of the code necessary to attach the sensor to the microcontrol unit and count the number of brakes within the IR field. This code will be used to determine the RPM of a spinning wheel and will be fed into the PID algorithm to create a feedback loop. The LCD can display multiple values on the screen. This will hopefully be used to display the RPMs obtained from the rotational sensor.
We decided to use a PID controller because of its flexibility. The PID algorithm is independent of our math model, which means it will still work even if the system's behavior is drastically different than we predicted.